Hello and welcome to another video. In this video we're going to be working on all 0-1 data structure, or all O1 data structure. And this one, you have a data structure that has the ability to store strings count with the ability to return the strings with minimum and maximum counts, and you have a bunch of functions. And so you have an increment function that increments the count of a string by 1, and if it doesn't exist, just give it a count 1. Then you have another one that decrements the count, and if the count is 0 after the decrement, remove it, and it's guaranteed that it exists before decrement. And then getMax returns the max count, just any element, and then getMin returns the min. And each function must run in O1 average time complexity. So for these, basically what you want to do, these are kind of like pretty difficult problems. There's a couple of these like LRU cache, LFU cache, all these things, where you're just trying to make a data structure that's pretty hard to do, and all your functions are in O1 or just some like small time. So for these, first of all, you can quickly figure out like what you can't use. So things you can't use would be like a heap, right, or like a binary search, or like a sorted list, or any kind of these things, because you have O1. So the things you can use are things like set, hash map, array, queue, linked list, things like that. And let's just say we had the simpler problem, right? For the simpler problem, it would be really easy. Let's say we didn't need this get max key or get min key. It would be really easy then, right? Because we can just have a dictionary with the string. So the key is like the string, and the value is just the count. And then it's pretty easy. We can just increment, decrement. That's all we need to do. But the difficulty is we need to get the max and min count, and things might get removed, so then max count and min count might like go away. So for example, if I put in an item and then I take it out, now there is no more max and min count, or I might go up too many or something like that, or like what if, like how do I know when I surpassed my max count and so on. So there's no really great way to efficiently store a max count, unless what you basically have to realize is to store the count, you need some kind of a data structure where you actually store like in some way the items with a count. And then that way the end of those items will be like the biggest, and then the start will be the smallest. And some things you could use here that would do the trick is like a queue or a linked list. So this would be more like a deck, where essentially the start of it would be the smallest item, and then the last one would be the biggest item, like the biggest count. And then that way we can pretty efficiently figure out what we need to do, right? Like imagine we have a linked list, let's say, or a deck, either one, where we store the count or frequency, and then a bunch of items in here, right? So linked list, something like this. And yeah, so let's say this contains like a frequency and all the strings in here somewhere. So then if we can somehow access, like given a string, if we somehow know where to look, then we can figure out what to do. And we also want this to be like if we use a deck or a linked list or something, or I guess for a linked list, we want this to be doubly linked, because we're either going to decrease or increase. So we might move like this way, or we might move this way. And so this is going to be a doubly linked list, or like I said, a deck, either one. Okay. And actually, I do think it needs to be a linked list, not a deck, because we're going to remove from the middle. So like, yeah, and I'll show an example of that. So let's say this is like frequency 5, and this is like frequency 1, and this is frequency 6. So you're not necessarily going to have, like, you're going to have some kind of linked list where like it's not all just going to be increasing by 1, right? It's not just going to be like we'll have something frequency 1, 2, 3, 4, 5, 6. You can easily have items that have these things missing. For example, if we insert something like A 5 times, then we'll have an A here. Then we insert something like B 6 times. So we just have like, we insert like, we go increase A, A, and then like B, 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 and then something like C. Now we'll have this thing, right? Where here we'll have A, here we'll have B, and then here we'll have C. So it's not necessarily going to be continuous. But if we want to modify the frequency of B, and we can somehow figure out what item it's in, then with a linked list we can do that. Because we can say like, well, if we want to increase it, let's just, because this has to be in order, let's just check like, is the next item of this a 6? If it's a 6, all we have to do is just move our B from here to here. Or if we want to decrease, we'll just say, is the previous item a 5, a 4? If it is, we'll move it in. And if it's not, then we'll make the node. So for example, if we have B's in here and we want to decrease the frequency, and we'll say like, well, the previous of 5 is not 4, then we'll make a 4 here. And then we can just simply move our pointers around to achieve what we want, right? So we can just do that. Yeah. So we can say like, let's just move our pointers around to keep our linked list structure, and then move our item here. So let's kind of walk through, one more thing. So how do you know, like given an item, like what node is it in? So you can actually use something pretty powerful called, well, not called, but you can use a hash map with a combination of a linked list to be able to access list nodes in O of 1. And the way to do that is your key can be whatever you want. In this case, it's going to be our string, and our value will be our linked list node. And then with a B, we're basically going to store B's value will be this node, and then we can access that node. So we're going to have two things. We're going to have a hash map of key value pairs of string to list node, and then we'll have a linked list that is going to contain a frequency number and a, so that's the other thing. We need to have these strings in a linked list, and we need to be able to get rid of them and add them in O of 1. So there's, I think, only one thing that lets you do that, which is a set of strings. And then we can access the first string in O of 1 using like an iterator or something like that. Because basically normally you access things in a set using like the key. But in this case, we just want one item from there, so we can use an iterator. So you could basically say like, you know, for string in strings, like give me first string, and break would be the equivalent of that. And this is basically using, you can use an iterator to get this first one. Yeah, so let's kind of walk through like all of the cases that we need now for these things. For this hash map, this linked list, like what's going to be our flow. And these things are going to be important when you're planning this out. Because like there's all these edge cases, so you want to figure out like when I'm inserting, what am I trying to do? Like what are the cases? How do I make sure I handle this? And this is kind of realistic to an actual like more work type thing as opposed to just like an algorithm. So let's walk through that. So let's say we're inserting a node. And we can just draw like a decision tree of like everything that can happen. So let's say we insert a node, or not insert a node, I guess, increase frequency. And hopefully you can see now that getting the max and the min is going to be easy with a linked list, because we can also just use a dummy header tail. So I always recommend this for linked lists, especially double linked lists. Just use a dummy header tail. That way, if your linked list is empty, you don't have any like edge cases you have to look for. So basically, we'll just have this. And this, you use this same kind of thing on like the least recently used cache or all those kind of problems as well. So we have this like dummy head, dummy tail, and then that way our max value will always be the previous of the dummy tail, and then our min value be the next of the dummy head. Okay, so those are going to be pretty easy, but let's figure out like what are all the edge cases. So if we insert a node, we can have two cases here, right? So one case is node is not in our hash map, right? Node not in map. And then we have our other case where node is in the map. Okay, so if the node is not in our hash map, first we have to put it in our hash map with a frequency of 1. So put in map with frequency of 1. And then we have two cases here. We're either going to already have this node with a frequency of 1, or we're not. So we can just check like if is the head next, does it have a frequency of 1? If it doesn't, we're just going to make it. So let's say this was frequency like 3. We would just make another node here with a frequency of 1. And then add that in, and then move our pointers around so the head will go to 1, we'll go to 3. And so that's what we have to do if the node is not in the list. So put in map with a frequency of 1, if node with frequency 1, not in list, add that first. And also, when you do put it in the map, you also have to put the node into the strings at this frequency of 1. So in here, like if we're inserting C, we'll put C in this thing. So we're kind of done with this side. Now, if the node is in the map, what do we have to do? So we have to check if the next node of our current node has frequency equal to our current frequency plus 1. Because if we increase the frequency of something, like if we increase from 4 to 5 or 5 to 6, it'll go up by 1. But let's say this was 4, this was 5, and this was like 10. Well now, so this node does, this like string has a frequency of 5, but we don't have a node with a frequency of 6. So if that doesn't exist, we need to create it. The same kind of thing. We're going to create it and move these pointers around. So then we will have 5, 6, then 10. So if the next node of our current node has frequency, or does not, or I guess has, and then this will branch into like a yes, no. So no, add, I guess yes branch, we don't have to do anything. So if no, and the same kind of thing, this is technically 2 branches, but I just wrote it this way. So if no, add a node after current node with frequency current plus 1, right? And then all we have to do is just shift it. So then all we have to do is just shift its like node that we're storing it in. So if we're moving from 5 to 6, all we have to do is remove it from the strings in 5, move it into 6, and also update this hash map to now point to 6. So this is basically all the increased frequency things we have to do. So we can add, like update hash map, update node. And that's the increased frequency. That's all we have to do. So now let's look at like the decision tree for decreased frequency. So the node will always be in the map when we decrease the frequency. But we will have some cases, like, for example, what if the frequency of the node is 1? Right? So frequency equals 1. So if that's the case, we want to remove from map, and it will always be in a node already. Like, right? We don't have to check if it's in a node. It'll always be in a node. It'll always be in our map. So remove from node, and then we're done, right? If it's frequency 1, this will guarantee exist. We just remove it from the map, remove it from the node, and then we're done, because we don't need to do anything with 0. Then we have the other path of frequency greater than 1. Then we update map as well. We have to update map no matter what. Remove from node always as well. But now we have 2 cases. So if our frequency is like 10 and we need to move to 9, same kind of thing. We need to check does 9 exist. So does the frequency before this one exist? So I guess we can just have one path here and just write that. So if frequency of current frequency minus 1 does not exist, make this node. Then move the string from cur to frequency minus 1, update the map, and all these things. So basically, if we were trying to move it from 10, we're saying, do we have a 9? If not, let's make the 9. If we do, let's just move it directly. And so there's all these things we have to take into account, and this is going to be important in the code. So just to recap, when we increase, if it's not in the map, we will add it to the map, and then we will put it in the node with a frequency of 1. If that node does not exist, we'll add it in. If it is in the map, we will check if the current node or if the next node of our current node is that frequency plus 1. If not, we'll make it. And then we'll basically, we'll always update the map, we'll always update the node string and so on. And then to decrease, same thing. If we decrease and it's 1, then we will just remove it from everything and then we're done. If we decrease and it's not 1, we have to check, is the previous node to the one we're in equal to that frequency minus 1? If not, let's make that node. Oh yeah, and one more thing. So whenever we decrease a frequency, like let's say we're decreasing this from 10 to 9, and this is the only node in here, if this becomes empty, then we also need to remove it. So we're going to be like adding and removing nodes a lot, and yeah. And then it's very easy to get the min and the max. We'll just say like, well, the min is just going to be any node in here, any node in head next, and the max will be any node in tail previous. So this won't be dummy, this will be tail. That way, no matter what we do, no matter like how we add nodes, like let's say these get deleted or something or whatever, it will always maintain this sorted structure. And so it's very powerful to use a hash map and a dictionary because it basically lets you access list nodes in O1, so you can delete from the middle of something in O1 because it's a linked list, but you can also access the middle in O1 because we have the hash map. So yeah, same kind of thing that you can use if you want to practice like LRU cache, LFU cache. I'd probably start with LFU cache, then do LRU cache. LRU cache I think is harder than this one, but it's the same kind of similar format where you're storing the count of an element and you're moving it up and down. Same kind of scenario, and you can do this in like a few other ways, but I think this way is pretty good. Okay, so let's take a look at the code. It can be kind of complex here. So we have our node, which is going to maintain the frequency and the set of strings and the previous and the next. And then we'll have the constructor for that. Then our constructor for our all1 is going to have the head and the tail, which will just have some values. And then the head next is going to be the tail previous is going to be the head. And like I said, I strongly recommend using a dummy head and tail because when your linked list becomes empty, the head just points to the tail and you can still insert elements easily between them. So it's very convenient, so you don't have to keep tracking like if my head is null, make it null, if my tail is null, make it null. It just kind of does everything for you. So like if everything's gone here, and then you always insert after the head and you can like do stuff here. And then you can check if it's empty by just checking is head next to tail, then you know it's empty and so on. So very convenient. And so this is the hash map of all the strings in the node they belong to. And then here we go. So to increment, this is what I was saying. So if it's not in the hash map, we will give it a frequency of 1. If that node does not exist, we will create it. And then we will add it to the hash map. We will add it to that frequency node. If it is in the hash map, then we increment its frequency. We remove it from the current place in the node. And we check, is that frequency plus 1, is it there? If it doesn't exist, we're going to make it. And then we're going to, regardless, update that node's strings. And we will also update the map to point to the new frequency node. So, yeah. And then, oh yeah, there's the one other thing that I actually forgot. So let's say we're moving a node from, so let's say we put in A with a frequency of 1 here. And we move it to 2. When we move it from 1 to 2, this will be empty now, so this is what we want to remove. So we can remove this when we move a node up or down. If this is empty, then we'll just remove. And then I just made a simple function called like remove node. So decrease, very similar to increase. So if the frequency is 1, we just remove everything. Otherwise, we check, is the node with a frequency of the current frequency minus 1 in the list? If not, let's make it. And then we simply update the node and we update the map. And then same thing, if we moved a node, if we moved a string from one node to another, if it doesn't have anything else, then we just remove that node. And then get max is pretty simple. So we just check, like I said, you can check if the list is empty by checking for the tail previous equal the head or the head next equals the tail. If either one of those is true, it's empty. Otherwise, we just get an iterator to the strings and we just return the very first string we find. Same thing here. So you can either do head next tail or this. Either one is correct. So this both works. Or do an iterator. And then the remove function is pretty simple. So we have a node. We just say the next node of its previous will be its next, and then this. So basically, just to show that. So if we have some nodes like this. So when you're removing a node from a doubly linked list, you don't actually have to update that node's pointers, but what you do have to update is the pointers of its previous node and its next node. So we want the previous node to not point to it anymore. We want it to point over here. And so that's this. And then we also want its next node to not point to it anymore, but to point over here. And so even though this node still points to these, because nothing points to it, it gets deleted. And then our list looks like this. So that's the idea here for remove node. Yeah, and then everything is O of 1. Sometimes we will add nodes, sometimes we will remove nodes, but even if we do, for the most part, if we move an item and add a node or remove a node, that's like one node and that's it. But the main thing is to learn how to use this data structure of the hash map with linked list combination to access elements in the middle of a linked list in O of 1, to remove them in O of 1, and so on. So yeah, actually I don't think you can use a deck because you can't remove from the middle of a deck in O of 1. Yeah. There might be other ways though with like multiple dictionaries and things like that. But I think this way is really nice. And then you can see it's pretty efficient. And obviously for complexities, so time, all of these are O of 1, space. So we have this is basically going to depend on the number of strings we have. So this is going to be like O of strings, because we can technically have like, a bunch of different frequencies. That's going to depend on the number of strings we have. And then we can have a bunch of like the hash map of strings, just how many strings we have. Yeah, you can see it's kind of long, and yeah, I mean, if you got rid of all the comments, it'd be like less. But this is kind of nice because it forces you to be able to like, this is kind of like OOP practice or something, I guess, because it's kind of like a longer one. You have to figure out a bunch of data structures to use, and also I had some like interview stuff that was like design like a trading engine or something like that, where all your stuff is as fast as possible. It's kind of similar to this kind of stuff, where you're making something not just like solve one problem, but design something that's like pretty efficient. Yeah. So hopefully this is helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.